So we're finishing off Chapter 7 with Section 7.4. It's been a long road, but the road continues. 7.4 is the normal approximation used to find approximate binomial probabilities. So we take the normal approximation and use it to find approximate binomial probabilities. Here we have a histogram of binomial. N is 40, P is 0.45. These are actually counts here, but with that, it's a really large sample, because this size here is 2,500, so I don't know how big it is. It's big. Does it say? It doesn't. It's big. So you would imagine the histogram be very close to the shape of the density curve, or this kind of very close to the actual probabilities, and also therefore very close to the density curve that approximates the binomial distribution. So in order for it to do a good job, we need NP times 1 minus P to be at least 10. So we'll see how good that is here. N is 40, and P is 0.45, and then multiply that by 0.55 to get 1 minus P. Look at that. 9.9. So barely okay. So I guess I didn't want it to get N to be too large because I didn't want to draw. This is already bad enough, all these categories, but when N is even larger, there's more categories. So 9.9, well, it doesn't quite make the cut, but it looks pretty good to me. And so as long as that looks good, I think we're going to be okay. If that looked jaggedy, then it's a little bit skewed maybe. It's hard to tell. I'm going to go for it anyway, because then I'm not going to do this with the N equal to 60, because then I'd have, instead of this many bars, I'd have 100 bars in there, and I just can't do it. Okay. So now we're trying to figure out the probability that of 16 happening. So that would be the area of this bar compared to the overall area as a fraction. So let's find the probability of x16, which is the fraction of the area in the shaded bar. We can approximate that, actually maybe, by the area under the density curve. So I've drawn the normal density curve that approximates the histogram. Because we said if it's big enough, the density curve approximates the histogram pretty well. Pretty close, 9.9. And we use the density curve to find the area under the density curve between 15.5 and 16.5, because that area then is an actual divided by a total area of 1. So it's the fraction of the area under the curve, or the probability of landing in that position, because the total area under the curve is 1 once you reorganize the scales. So that curve has mean. So the normal approximation to the binomial, you just take the mean for the binomial, that's its mean. So N times P is 40 times 0.45. I'm going to regret this in a minute, I can see that. 40 times 0.45. Oh, 18. Oh, that's nice. Someone thought ahead. Didn't want to round anything too much, but are we going to? Not that much. Well, we'll have to compute C, but big deal. And the standard deviation, 40 times 0.45 times 0.55 is this. And take the square root. So 3.1464. 3.1464, which is the square root of 9.9. Because NP1 minus P is 9.9, and this is the square root of NP1 minus P, so that's okay. And then we're going to find the Z values, one for 15.5. So Z is x minus mu over sigma, okay. 15.5 minus 18. If I could write it would help. 15.5 minus 18 over 13, the mind, 1464. And here Z is 16.5 minus 18 over 3.1464. Okay. Making progress. Those are both below the mean, so I expect the Z values to be negative. 15.5 minus 18 gives you minus 2.5, and you divide that by 3.1464. Okay. Minus 0.795. minus 0.795, like that. And now I do it with a 16.5, minus 18. So that's minus 1.5, that makes sense. And we divide that by 3.1464. Okay, minus 0.477. So we have to round these. So I'm going to go minus 0.80. I'm going to minus 0.48. Like that. And then I'm going to go to the tables and subtract. So for the one that's going to give me the biggest area is the largest z-value, the one furthest to the right, which should be negative 0.48, the least negative one. Negative 0.48 gives me 3156. I lost what it was. We said negative 0.48. 3156. And then negative 0.8. 0. 2119. So 0.3156 minus 0.2119. Okay, so now I'm going to compare with the real answer, see how we did. It says 0.1037. The true probability that x is 16, binomial, came out to be 0.104334, like that. So we're pretty close, 104 rounded, 3 places, accurate. Right, so that's using the normal approximation to find a particular value, but you could also use it to find a range of values. I'm going to leave this picture because it's so hard to draw, and we'll do a new calculation on this side as soon as we save this video and start making a new one.